Hi everyone, this is Super CEO, and today I've got two questions that are unfortunately only found in the Extension 1 version of the Cambridge textbook. So let's have a look at those two. And before I do that, so here's the statement that I usually post up at the beginning of my video. Okay, the two questions that I mentioned that are only found in the Extension 1 textbook are these two, question 11 and question 12. Okay, all right, so just because you're doing 2 unit or advanced course doesn't mean that you don't have to watch this, but if you're interested, you're more than welcome to watch and pick up some skills there from these two questions. Okay, so the very first question of the question 11, the first part is, as usual, given the frequency function for such domain, and notice this one is not a confined domain. There's no end at the larger values of x, so 1 all the way up to infinity basically. Part A, so just to show that the little f of x function as given is actually equal to that. Okay, so that's the first part that you have to do. Now, what I'm going to do is show that that is equal to that one that's given in the first place. So that's basically, doing the common denominator stuff. So that's all that, right? And hence that. Okay, so pretty easy exercise there. Part B is now show that this f of x, the integral of that f of x, is the primitive for that is actually this. Okay. So if let's do this. So that's that one. So instead of using that, we're going to use that. All right. So that was really part A was 4. So it's easier to work with. All right. So that's this. That's a constant, so you can take that out. So, individually you can now integrate. Okay. So that's this. All right. And that one, notice also the the derivative of the denominator here, x plus 1 is still 1. So that perfectly fits in there. Okay. I mean, you're supposed to have absolute value of x around x plus 1 and the same here for x. But in the domain, you were told that x is x is greater than or equal to 1. So you might as well drop the absolute values. So that's that. And now as you can see here, 1 on ln2, 1 on ln2 serves a common factor. So you can take that out, put it into one bracket like that. And remember, one of the log rules says that when you have the same logs with the same base, and two logs are subtracted, then you can basically take those two as a division. So that's that. Okay. Now, strictly speaking, we should have plus c at the end, but the integration constant here doesn't really matter because later on we're gonna have to look at the PDF property of it. So that's why we can pretty much ignore that. Now, part C, that's to show that the little f of x is actually a PDF. So we know that ln2 is a positive, so the reciprocal of it is still positive, all right? And we also know that x times x plus 1 is positive because of the domain, okay? So therefore, the reciprocal of it is still positive, right? Hence, the first condition of the PDF is satisfied. Now the integral for the definite integral in the domain of the function, which was x greater than or equal to 1. So we might as well take the integral from 1 to infinity, which is that. Okay. So remember, where do I get that from? Just above here in part A, we've shown that that is equal to that. So and we've also shown that, we've just in part B, sorry, my bad. In part B, this integral, the indefinite integral, is equal to this one. So now to get the definite integral, you just gonna have to take this and evaluate it from 1 to infinity. So that's basically what I'm doing here. Yeah, and then, as usual, instead of working with the infinity, we take that into the limit notation. Okay, and replace the infinity with the m and let m go to infinity, basically. So do all that, you get this, that, and that. Okay, all right. Now, the reason all of a sudden I have from minus to plus is because, again, one of these index rules, so I explained it here, ln half is actually minus ln 2. So minus of minus becomes positive. All right, so that's that one. That's the reason why I have plus there. And now this here, what makes me say that this is equal to ln of 1? Well, notice the degree of the numerator is the same as the degree of the denominator, and the coefficients are the same as 1. So therefore, the limit of it is just ln of 1. Or you can think of it this way. As m gets really large, right? So you can pretty much ignore the plus 1 term in the denominator. So you can pretty much ignore that. And then at the larger value of m, this fraction almost behaves like m on m, and we all know that that's just 1. So that's ln of 1. Okay, and that's ln of 1 is actually, or log of any 1 is actually 0. So therefore it's just 1 on ln2 times ln2, which is 1. Hence it's a fair income PDF. Okay, all right, now part D, the expected value, you just got to multiply the given frequency function with the x. Okay, so again, noticing that 1 on ln2, I can take it outside the integration and multiply those through. So then you get this and that. All right, and then a bit of common denominator exercise here to get this. Okay, all right, and then a bit of cancelling with the x terms so that you get that. Okay, and now the substitution. And well, again, this here, we know that the derivative of x plus 1 is 1. So therefore, I can put that as an ln of x plus 1. And evaluate it from 1 to infinity. So same trick with the use of m. And you get that one. But unfortunately here, as m goes to infinity, that whole log function blows up. So remember, because the log function behaves like this. Okay, so as x gets really large, the log function itself gets large, very large too. Okay, even though it's at a subdued growth rate, it's still growing. So that's almost infinity. Hence, the expected value does not exist, because that's an infinity, not a fixed number. Okay, so that's question 11. Question 12. Okay, so you have to show that this definite integral ends up being pi. Well, let's have a look. So that's that one. But we all know that the integral of 1 on 1 plus x squared with respect to x is just tan inverse. And you can see that you can also get that information from the reference sheet. Okay, so now tan inverse function looks like this. Okay, so as you can see that as x gets really large up here, the tan inverse function converges to pi on 2. And when it's negative infinity, then it converges to negative pi on 2. So that's pi on 2 minus pi on 2. So that's 2 pi on 2, which is pi. Okay, so that's proved. Part B, again, we're trying to show that this little f of x function, which is that one there, is a PDF. Okay, so let's have a look. So we know that pi is obviously positive, hence the reciprocal is positive. 1 plus x squared is always positive, no matter what value of x you've got. because it's squared, and then you add the ones, it makes it even more positive. So the reciprocal of it is still positive, so multiply them, you get positive. So that's that one. Now the definite integral from negative infinity to infinity is that one. You can take 1 on pi out and this, but remember here, we know from part A that that is equal to pi. So that's my little justification there. Okay, from part A. So hence that's 1. Hence this is a PDF. The expected value. So you multiply this time this function here, the little f of x function, by x. So then you get this. Okay. So that's that one. 1 on pi out. But why is it 2 there? Well, because I noticed that the derivative of 1 plus x squared here I mentioned is 2x. So I have to have 2 in front of x. So I've created 2 out of thin air. Therefore, I need to divide it by 2 at the end to make it the same with the above line. Okay, so that's the consistency matter. So that's that. Hence now that's ln of 1 plus x squared. Notice I don't have to put the absolute values there because 1 on x squared itself is always positive. So that's that one. Substitute there using the limit notation. Then you get this and that. All right. Now, this here, exactly the same. Okay, 1 plus, I don't care what the m is, it's 1 plus m squared, and you've got 1 plus m squared. They're getting subtracted. So that's the limit of 0, hence that's 0. In other words, the expected value for that continuous variable x is 0. Okay. All right. Or you could do it this way. Again, that's the expected value, x times the primitive, sorry, not the primitive, the little frequency function, which is this one. Multiply that by x to get this. But you know that this is an odd function. How do I know that is an odd function? Well, the denominator, sorry, numerator here, x, y equals x, is an odd function. And y equals 1 plus x squared is an even function because that is symmetrical. It has a rotational symmetry around the origin, and this one has the line symmetry about the y-axis. So, odd function times or divide by an even function is still an odd function. So odd function with the symmetry values being evaluated, that's always going to give you 0. So that's 0. Okay, so that's another quick way of doing that. And finally, the variance is sigma squared, which is this time you're going to have to remember that that's the practical definition, which is E, the expected value of x squared, take away the square of the expected value we got. So that's this formula. So notice that's x squared now, not x. All right, so now where do I get that from? That's given in the question. So here you were told that in last part you have to use that identity in part D. Okay, so that's this one that I'm talking about here. So I'm using that identity right here. Okay, sorry, here from this line to that line. Okay, using the hint given. Hence now I have that. All right, so separating the two into two independent integrations to perform, and now that's just this and that one there. Again, that's from part A. Okay, so now this gives you that, and evaluate it, I get this because it's m minus m, which is 2m, take away 1. But unfortunately this here, as m gets bigger and bigger, 2m gets even bigger. All right, so that blows up to infinity, hence unfortunately the variance doesn't exist, just like in the previous example. All right, so that about does it for 16C, and the next video I'll have a look at questions 16D or 10D, and then have a look at some enrichment questions. All right, till then, see you guys next time.